Good morning, good afternoon, and welcome to our latest online seminar with a new title today, Secure Private Keys in Public Firmware and Best Practice for Embedded Trust. My name is Max Kliemann, leading the sales team here at ONEKEY, and joining today with me is Sebastian Schneider, who is our customer success engineer. The agenda, quite simple. I'll start with a very short introduction. Who is ONEKEY, what are we doing, and why are we the experts in the embedded field? Handing it over to Sebastian for the technical part, who's giving us a short refresh on crypto basics and certificates, and then a little bit of best practice and pitfalls. We will end it with a question and answer, a short Q&A session, and so please make sure that you put your questions in the lower right corner on the questions tab. It's right left next to the chat field. Yes, so I think we are good to go. Lots of people on board. Let's start. So it always starts with a challenge, and when we look at the product security challenge, we basically see three major trends who are driving this topic. First, obviously, we do have the technology trends. We have over 50 billion smart devices in the field, and this number is continuously rising through trends like autonomous driving. We got smart cities, smart energy, industrial Internet of Things, or anything that is connected will increase that number. Secondly, we see increased amounts of attacks through hackers. And more they're exploiting smart devices, and we're not talking about individuals here, we're talking about criminal organizations which are protected and financed by states. And last but not least, we have regulations. We have our government who is trying to protect us as individuals and our companies against these attacks by increasing the complexity of regulations around the world, and this just adds more complexity to the whole product security challenge. With that said, where do we start? So when we want to start our product cybersecurity challenge, first what we need to know is obviously what's inside our product. We need some kind of software ingredients list. We need a secure software supply chain. With other terms, we need a software bill of material, an SBOM. And the accuracy of that SBOM is important for all following tasks, when it comes to our product cybersecurity journey, because it significantly influences how successful we are going to perform vulnerability and compliance management within our organization. Especially when it comes to vulnerability management, this is something we're going to talk a little bit more today. But in a nutshell, what ONEKEY does is we perform static binary code analysis. So we generate the SBOM from the binary image in minutes, and then we check for vulnerabilities. We check for known vulnerabilities, CVEs. We then reduce the amount of false positives through an automated impact assessment, and then we check for unknown vulnerabilities like private keys. And all this can be monitored throughout the product lifecycle 24/7 and can be seamlessly integrated in your CI/CD pipeline through our API-first approach. And then if we have checked for vulnerabilities, we can then map these findings in our analysis against our compliance wizard, where we map it against security regulations like the EU Cyber Resilience Act or the IEC 62443. Obviously, we like to do a lot of automation, but we know automation has limits. So when we do face that limitations, we come in with professional service where we support our customers around the product security lifecycle, from the concept to the design phase till end of life, on the process level with gap assessments, and on the product level with some services like manual penetration tests. With that said, that's the introduction of ONEKEY. I would like to hand it over to you, Sebastian, giving us more interesting insights on the topic today.
Yeah, thank you, Max, for the kind introduction. My name is Sebastian Schneider. I'm customer success engineer. And today we want to talk about private keys, about certificates, and all the important bits and pieces. And finally, we will also jump into our platform and see how automation can help you to avoid certificate-related risks in your device. So why is it important? Already 10 years ago, a study found out that millions of devices are running with the same keys installed on it, obviously installed by the firmware. And if one of these keys will breach, then all the devices are at risk. So as I said, this was 10 years ago, but also more recent findings like this from 22, where even the big player showed that they still have some legacy protocols and some legacy mechanism to encrypt and decrypt configuration files on their devices and use static hard-coded keys for this matter. And here we have the most recent case from 2 months ago, where a voice over IP telephone provider was, or telephone vendor was found that they have a hard-coded private key for a root certificate baked into a firmware so that the device could reissue expired certificates by themselves, which of course is also a great weakness. And if you don't yet understand why this is a problem, we will see this in this talk today. So, but before we jump into the certificate topic, I would like to give you a quick refresher on crypto basics so that we are all on the same level. Bear with me, we don't do too deep crypto stuff today, just scratch the surface. So we start with a file here, and when we calculate a hash value, this hash is unique to this file. You could say it is like a fingerprint of the file. And if you now copy the file over to another system or send it via email, and the file content is identical, the hash value will not change, and the file can be recognized by this hash value. So some requirements for hash functions are that they are unique, that they are collision resistant, which is basically the same. So no two files are allowed to calculate the same hash. And they must be one-way functions. So it is not possible to recalculate or recompute the original content of a file just by observing a hash value. So now what happens if a single bit or even more changes in a file? Then the file will generate a different hash value, and it can be immediately detected that the files are no longer the same. Even for small changes, even for very large files, a single bit flip can be detected by the different hash value. So now to protect the integrity of a file, you could store this hash value alongside with a file, or also send the hash file via email or over which channel you choose along with the file. And if something breaks during storage or during transportation, you would be able to detect it by comparing the current hash with the stored hash value. So corruption can be detected, but of course the problem is if this is not an accidental corruption, but if there's an attacker, someone who intentionally modified the file. Because we can assume that if someone is able to modify the file, they also can modify the according hash value so that both file content and hash again fit together, and so the modification would not be detected. So that's of course a weakness of just having hashes alone. Jump to another topic, symmetric encryption. So this obviously protects the secrecy, the confidentiality of files, we again start with a single unencrypted file. We now need a secret key. And if we apply an encryption function together with a secret key to the file, we end up with an encrypted file, and we need the same secret key to decrypt the file to receive the plain text again. So if we now have, of course, Bob and Alice, they want to exchange a secret message. They first of all need to agree on a secret key. So here Bob sends his secret key to Alice. She can use the secret key to encrypt the file and send it back to Bob. But here, of course, the weakness is that they already need a secure channel to exchange the secret key. And perhaps if they already have such a channel, they could use it to also exchange the file without the need of additional encryption. So then perhaps the asymmetric encryption is a better choice. Here we no longer have the secret key, but we have a key pair. They are called public key because it is actually public, and a private key that must be held securely. So if we now have this file again, we want to encrypt it, we can use the public key, and only the private key will be able to decrypt it and to receive the original plain text again. So if Bob and Alice wants to exchange secret message again, Bob can first send his public key completely without encryption over via email, and Alice could use this public key to then encrypt the original file, and only Bob with the private key can decrypt and receive the original data. But also the other way around would be possible. So if you use the private key to encrypt the file or data, everyone with a public key will be able to decrypt the data. And why this is a very important feature of asymmetric encryption, we will see in the next topic, certificates, because there it is heavily used to build a chain of trust. So certificates. How does it work with certificates? One of the biggest shortcomings of simple public-private keys is that they don't hold any identity. So even if you have a bunch of public keys, you can't directly distinguish who is owning this public key. And that's where certificates come into play. We add data to this public key, especially who is owning the key, who issued the certificate, and certificates typically also have a lifespan. Now to bind this information to the private key, we again generate the hash value of everything together, so data plus public key, and we then private key encrypt this data. This will generate a so-called signature. And of course, after using the private key for generating the signature, it must be securely stored away. So here the recommendation is to really store signing keys on an offline system, and yeah, don't expose them to any risk to be somewhere copied. Best, of course, is to have a hardware security module to store such keys. So signature will be added to our certificate, and we now have a full certificate. If now someone wishes to validate the certificate, they can strip down the signature. So we end up with the original combination of public key and data. They can compute the hash value of this package and use also the public key to decrypt the original hash value. If now someone would have tampered with this certificate, would have exchanged the public key or changed any data that are included in the certificate, the signature would no longer be valid, because the self-computed hash value and the decrypted hash from the signature would no longer match. So that's how certificates are validated, at least on a cryptographic standpoint. Of course, validation also includes checking the validity, if it is already valid and still valid, and to check if the issuer is trustworthy. So already speaking of the issuers, certificates have different data fields. The first is here the issuer. We see we have something like a country code, organization is Trust Me Limited, common name, very important for certificates. So this is who owns the certificate. In this case, it is the Trust Me CA. CA stands for Certificate Authority. And here is something special. You see that issuer and subject are identical. This is always the case for a self-signed certificate, and this self-signed certificates build the root of trust for such a certificate trust chain. This could be a self-signed certificate by your organization that is only internally trusted, but it could also be a trustworthy, well-known organization like Microsoft, like Google, like Global Sign, which also have self-signed certificates that are used to issue sub-certificates, but the industry agreed that these companies are trustworthy, and so these root certificates are shipped as part of your operating system or as part of your browser, so that they can be used to validate further certificates. Then here we also see the validity period, in this case, like 11 years. So this certificate can't be used after 2035 to sign further certificates. So now I already talked about certificate signing. How does this actually work? Here we see a new certificate signing request. And the first thing I want to point out is that this is using a different pair of public and private key than the original root certificate. They have individual keys here. Then we see the issuer field is pointing back to the root certificate, while the subject is an individual subject, still the same country code, the same organization that is not necessary. In this case, I choose to put it there. And then important, the common name is Bob. So this is Bob's certificate, and everyone who trusts the issue certificate can verify that this is that the certificate is issued for Bob. Yes. So now we need to take our private key from the root certificate out of a safe, compute the hash value of this certificate signing request, and use it to generate the signature. The signature is then added to this signing request, and it will become a full certificate. If we now want to verify that this certificate is valid, we use the public key from the signing certificate to decrypt the signature and regenerate the hash value so that we can compare it with the data and public keys hash. So, but of course, it is not always so easy that we have a root certificate and directly leaf certificates. In practice, we see that we have a certificate authority, which has one or multiple intermediate certificates. If you're looking at an organization, this could be one intermediate certificate per branch. Or if you think of device certificates, you could have one common root certificates and then intermediate certificates per product family. And this certificate then can be used to issue individual device or person certificates. And the idea here is to actually protect the root certificate. So even if one of your signing keys from the intermediate certificates breaches, it can simply be revoked so that all the leaf certificates of the one branch will be invalidated, but the rest of your structure will not be affected by this incident. So what are typical use cases for certificates? Of course, I already mentioned it, device identity and authentication. So it is quite common to have embedded devices, industrial automation devices that already have a built-in certificate, perhaps with a common name set to the serial number, so that they are individually identifiable by the certificate. Mm. Then, of course, certificates are used for secure communication like TLS. We have HTTPS. So if a device has a web server, um, perhaps for configuration changes or for some logging, then and it offers HTTPS, you need to have a certificate and a private key installed on the device to enable HTTPS. For MQTT, typical cloud protocol, the MQTT server will very likely run on HTTPS, so that the device must use a trusted root certificate to validate the server's identity. In some cases, we also have mutual TLS in such a setup, so that not only the server has to present a certificate, but also the client. Then we have some industrial protocols that are already TLS enabled, like Secure Modbus or OPC UA, and of course VPN like IPsec and OpenVPN, while I'm not quite sure how widely spreaded WireGuard is in commercial and industrial setups. And then, of course, you can use certificates for firmware signing. So here you would install a trusted root certificate in your initial firmware where the device is initially shipped with. And then for a firmware update, you use a software signing certificate, of course, inherited by this root certificate, to sign the firmware again by calculating the hash of the finished firmware package and then private key encrypted and adding this signature to your firmware so that the device can use the installed trusted root certificate to verify, first of all, of course, the certificate chain over some potential intermediate certificates till it reaches the root. And then, of course, also checking that the signature is valid and nobody tampered with the firmware update. We have already seen certificates have a lifespan. So for root certificates, typically 10 to 30 years, of course, depending on the use case, this can be different. Intermediate certificates are typically valid for some years, also dependent. And it is quite important if you need a new certificate to plan with overlapping validity periods. So it can be quite stressful if you need to update certificates on multiple devices and you roll out somewhat stacks and then certificate expires and suddenly all communication is blocked to these devices. So really plan with some spare time, some overlapping period when you need to renew certificates. And then we have the leaf certificates, typically valid for something between a few days and years. Again, of course, the lifespan is always shorter than the issuing certificate. Also here, it's important to have the overlapping lifespan so that the renewal really goes smoothly. Speaking of which, certificate update is a quite important and critical topic. You could try to manually update certificates, but you can imagine if you have hundreds of devices out in the field, this doesn't scale. I've seen some implementations that use MQTT to update certificates. Definitely possible, but more on the self-invented side. Then Microsoft has a certificate enrollment web service, typically used in corporate networks. The automatic certificate management environment or ACME protocol is used by Let's Encrypt to issue web server certificates, could be eventually ported to IoT devices. But today we want to look into enrollment over secure transport, which is also defined in the RFC 7030, because I think it is a quite neat protocol for certificate updates and also bootstrapping. So let's jump into it. On the left side, we have an IoT or OT device, which has a factory installed trust anchor and a vendor device certificate. It is also running the EST client, and the EST server and the certificate authority are running in the customer's or asset owner's network. And when the device is connected to this network for the first time, it will establish a mutual authenticated TLS connection to the server, which means that the server has to present a server certificate, but the client also has to authenticate itself with the vendor device certificate. If this works out, the device will send a request for an updated version of the CA certificates. So it will then invalidate the initial trust anchor and install the received CA certificates as new trust anchor. So now we installed the asset owner controlled CA certificates as new root of trust in the device. The next step is then for the device to generate the key pair, public key, private key, and a certificate signing request and send it over to the EST server. The server will then validate the signing request, and if everything works out, it will send the signing request over to the certificate authority. How this back-end communication works is not defined in RFC 7030, but there are already working implementations that do this. If this certificate authority is also happy with the signing request, it will send over a signed certificate, and this will be then handed over to the EST client and installed on the device. So then the initial device certificate will also be invalidated, and the device has an asset owner controlled certificate for its device identity. And now, of course, when the certificate is going to expire, the same process can be started again, but this time, of course, already with the asset owner controlled certificate to renew the certificates. And if a device gets decommissioned, this can be also registered on the EST server. And then if someone comes with this decommissioned device certificate, it would reject the request for certificate signing. So let's look into some best practices and pitfalls in certificate handling, and especially private keys. You should always use unique device certificates. No shared certificates. Of course, you can share a trusted root certificate without a private key in your firmware, but if it goes to device certificates, every device should have its own certificate and its own private keys. I already mentioned it, establish a proper public key infrastructure with offline root CA, so protect your signing keys by not connecting it to any network connected system. Follow standards. There's a technical guideline from the German BSI, but also other guidelines that exactly say you which fields are important, which settings you should choose while generating certificates. Also for device certificates, you should store the private keys in secure elements or hardware security modules. There are some also quite cheap one, just costing a few cents, that should be integrated in your layout. Support, of course, certificate renewal. We have seen one method with the EST protocol, how this could be implemented. Then if you already automated it, you can also opt for short lifespan, regular certificate rotation, so that you can, every time when you reissue a certificate, validate if this device is still allowed to connect to your network and the other systems in the network. This is very important, separate development and test certificates from production certificates. You should, of course, practice all the steps like device certificate issuing, renewal, firmware signing in your CI/CD pipeline, in your QA processes, but you should definitely use test certificates that are not valid anywhere outside in your production devices. Then integrate secret scanning in your CI/CD pipeline. And that's something I will also show you in our short demo. So stay tuned. Now come to the pitfalls. Don't hardcode private keys into firmware. We've seen why this is a bad idea. Don't reuse one certificate across devices. So again, really use individual certificates. Don't ship long-lived certificates without a renewal path. We have seen how this could be possible. Don't let firmware updates override your keys. So, of course, the easiest way is to have a secure element which stores your keys so it will not be affected by any firmware update. If this is not possible, you need a persistent storage region to store those keys. Best, of course, somehow encrypted, then with a device individual encryption key. And this persistent storage region should not be affected by your firmware updates. Don't use weak algorithms. So this is another thing. You should follow standards. There are also some technical guidelines on key lengths and cryptographic algorithms. And here we have a list of really deprecated and unsecure algorithms, so try to avoid them. Then another thing is if you generate your private keys on embedded devices, the random number generator often have a quite poor randomness, so the keys get predictable. Again, a strong reason to use some hardware security module with integrated random number generator to improve the quality of the generated key material. Don't mix test and production certificate. I already mentioned it. Really make sure that the test certificates are not trusted in your actual releases. And also very important, don't try to hide or obfuscate keys in the firmware. Use real protection like hardware security module. And of course, yeah, don't put them in your firmware. So let us jump over to our platform. And I have prepared some firmware. So I used Yocto and I included my own certificates. So nothing bad will happen if I show you the private keys here. What do we do? Max already mentioned it. We use binary firmware. We analyze it, scan it, to a software composition analysis based on the found components. We can identify CVEs, but then we also go a step further and look for previously unknown issues. Let me quickly show you the features. So first, we extract the firmware. Here we see the basic structure of the firmware, how everything gets extracted. The next step is to reconstruct the root file system. So here we see the Linux typical folder structure with a bin folder where all the applications are installed. We see that we already categorize these binaries. We see what is an application executable file, what is a symbolic link. And with this knowledge, we go to the component detection and automatically detected here the 28 components listed here with a version number, if applicable, and the CPE string. CPE is this piece of information that is used to link a component to publicly known vulnerabilities. But of course, already at this stage, you can download a software bill of material in different formats with all the necessary information. Looking at CVEs, so here we see it is a quite recent system. It only picked up 36 vulnerabilities, or if I remove this filter, 52. So what happened to the 16 vulnerabilities that are hidden behind this bar? Our platform does an automatic impact assessment and can flag vulnerabilities as false positives. So we see here our match score. And if I apply this filter, the negative match score will disappear. And if we look here, we see how this match score is calculated. So for example, we have seen in the metadata of the vulnerability that it is affecting x86 architectures, while the firmware was compiled for ARM. So we have a very strong evidence that this CVE is irrelevant for the given firmware. We then, of course, can also filter by severity, by attack vector, so only looking at network-based attacks, and by exploit maturity. So if there is a known exploit in the wild for this vulnerability, and we end up with one vulnerability, I haven't further triaged it, so I can't actually tell you if this is a problem for this firmware. But looking at the time, let us quickly jump over to the issues section, because here we actually detected some certificate-based issues. We, of course, have the hard-coded root password, or even worse, we have an empty password for the root account. So this is a finding from the platform. But we also detect multiple private keys or certificate with private keys within this firmware. We show you here exact details in which file the key was found, the OpenSSL output, the fingerprint of this certificate, so it is uniquely identifiable. And what is really important here, we detected a private key in a binary. So also this is possible if a key is statically compiled into a binary file. Here we see it. It is wrong file. This one, TLS server. It is an application elf executable compiled by me, but here we see it has some hard-coded certificate and a hard-coded private key baked into this executable. But that's not all. We also detect things like trust mismatches. So here I generated a fake Let's Encrypt certificate that doesn't match our golden copy of trusted certificates. So here we have a trust mismatch, and we also flag expired certificates. So here Yocto also installed some expired certificates. It was completely unnecessary that I forged also an expired certificate, but here we can see in the output that it was only valid until last week. Yeah, that's it from my side with the demo. Perhaps we still have 4 minutes for a Q&A. Max, are there any questions?
Yeah, there are. Thank you very much, first of all, for that technical introduction. We do have 3 questions. First one is from Jonathan. Hi, Jonathan. Nice to see you again. Are there any strategies to update root of trust in maybe offline embedded IoT devices due to the limited validity period?
Offline, of course, is quite challenging. I think then if it is not connected to anything and the update path is not already built into the device, you really have to manually update the devices. There is a technique called cross-signing, where you sign the new certificate with your old, still valid certificate, and the old certificate or root certificate with your new root certificate, so that they both appear to be intermediate certificates of each other. And this can really help you to streamline rollover of your root CA, so that they are still valid certificates even for devices where only the old certificate is installed.
Thank you very much, and hopefully that answers your question, Jonathan. Then we have one from Marie, who would like to know how to keep track of all the keys and certificates.
Yeah, very good question. So in the same manner as you have a software bill of material, you could also have a cryptographic or crypto bomb. We also help you here with our platform. So we actually list all the certificates that we detected in a firmware. So this could be really your starting point. We also list private keys, but usually you shouldn't find any private keys. So this is actually an issue. Yeah, but this certificate listing could help you to keep track which are already on a device. And then, of course, you need to add your documentation of all the keys and certificates that you use during testing, development, and production.
Thank you. Then we have quite a specific one from Cleo, who is probably using Diffie-Hellman for exchanging symmetric keys with a temporary secret. You want to know if that is a valid approach.
I'd say it depends. If it is like a self-invented mechanism, I would recommend to switch over to some library that does something like this. Yeah, can't really say without knowing the more details. But it sounds a little bit like self-invented, and if this is the case, I would recommend to switch over to a more standard approach.
Thank you very much, Sebastian. Maybe a good good starting point for discussion after the seminar. And then last but not least, we have one from Paolo. He would like to know how we can provision the secret key needed to decrypt the new firmware update package on a legacy device already in the field, without relying on transitional firmware update that temporarily exposes the device to private key.
Yeah, this is a typical chicken egg problem, and we have seen that it failed in the wild. I don't know of any other approach than having like an encryption key hidden in an intermediate firmware update. But of course, someone will notice and will be able to find this hidden key in this intermediate update. I think there is no good approach. The actual question should be, why do you need to encrypt a firmware update? Perhaps to protect intellectual property, but if it is more for protecting the integrity, you should think about firmware signing, because then you don't have to hide any key. Yeah.
Okay, thank you very much, Sebastian. We have more questions coming in. So we got two from Stefan. We start with a longer one. You previously stated that the cert contains only the public key plus meta information. In your demo, you showed detection of certs, including private keys. That is confusing him a little bit regarding the definition of a cert and what it is containing.
Yeah. Okay. Perhaps I didn't. I wasn't clear in my demo. So I intentionally included the private keys a little bit as what's happening with my platform. Never mind. So I intentionally included these keys to show you that the platform is capable to pick them up and show you that there is an issue. But usually you shouldn't find these private keys in your firmware.
Fair enough. So now, last but not least, from Stefan again, this one I can even answer. So what sources do we use for the CVEs? This is only relying on the NVD. If we do have anything else, short answer is yes, but the long answer is that we are currently working on, including different data sources. We're also looking at the European one, and we should be able to have more data sources by the end of Q4.
Nothing to add here.
Awesome. Thank you very much, Sebastian. Yeah, last but not least, if you like the seminar, please make sure you follow us on LinkedIn to get the latest insights. Usually we do have the next online seminar written in here, but it will come soon with more information. So yeah, make sure you follow us on LinkedIn, and thank you very much for today's session. Bye-bye.
It was a pleasure. See you. Bye.